All right, let's see. Looks like everyone's pretty much here. All right, that's good. All right, we may as well get back to where we were. So we were doing chapter 1A actually, and we were looking at functions the whole time. So we had a few functions that we were starting to look at. So why don't we take a step back here and start again with the basic functions. And so we're going to look at these one at a time, and we'll notice that each one of them has very different properties that are very interesting. And so we'll just carry on from there. So this is 1A. We'll probably also get into 1B today. And along the way, I also have a few very interesting videos that we can look at when an opportunity presents itself that are really more about the history of math than anything else, which is always very interesting. So we'll do that. But first, let's get back to the new material. And so we'll start out again by reminding ourselves that there are several important functions that we need to be familiar with in pre-calculus. And so we saw some of these last time. We have, for example, the constant function, identity function, absolute value. Let's see, what else do we have here? Oh man, there's a lot of them. A quadratic function, cubic, reciprocal squared. So square root and cube root. Now, of course, this is just the beginning. There's many others as well, but these are the most important ones. These are the ones you'll see all the time in pre-calculus and calculus and really any other math class that you might run into. So it's important to have a good feel for how these functions work so that no matter what you try to do with them in the future, you'll have a better understanding of their intrinsic properties. All right, so anyway, I just want to remind everybody before we get started that we only meet once a week, which is kind of weird. So it's easy to forget what we were doing last week. But don't forget that all the classes are recorded. And you can find our notes underneath in my YouTube account. So what you have to do, though, is go to the playlists. All the videos are sitting here, but they're all kind of jumbled together. So what you want to do is go to playlists and look for our class, which is, well, God, where are we? That's interesting. I'm not seeing it. There it is. No, that's not it. Wait a minute. We're Math 1150. And I don't know. It doesn't seem to be here. That's very bizarre. All right. I'll look into this later. Oh. No, you know what? I don't know what happened here. I know I created a playlist for it. Well, you know what? Let's take care of that right now. I wanted, let me just go get my copy of all the Zooms and see what happened. Okay, this is it right here. Well, you know what? All right. Well, I don't know what happened, so I'm going to put it there now. I'll put it back. Let's see. This takes a while. Let me just quickly put this in the proper location. So what I have to do first, it has to be converted to MP4, and then it has to store it basically, and then I have to manually place it in our account. So let me just get this taken care of right now. And then you'll be able to watch it whenever you feel like it. So I do not. All right, so this is going to take a while, but before the class is over, I'll be able to post this into our playlist, and then I'll do the same thing with today's class. Yeah, there it is. Yeah, I don't know. So, all right, we'll leave this going for a while, and then, okay, let's get back to it. All right, anyway, especially a class like this where we only meet once a week, it's awfully important to have access to the recording so you can refresh your memory. So hopefully that won't happen again. So anyway, so let's take a quick look at some of these functions, and some of them are really quite simple. Like here's a good example. A constant function means exactly what it sounds like. The function is always equal to that same constant. And so what you're looking at here is basically a horizontal line. Like, for example, if the function is x equals 5, that means that y rather equals 5 no matter what the value of x is. And so it's a horizontal line, and it goes on forever in both directions up to positive infinity. On the right-hand side, as you know, the real number line goes up to positive infinity, and down here it goes down to negative infinity. Okay, and then we're done with it. The slope, and also the slope, while we're at it, the slope of this line, which as you know is delta y over delta x, you can see that y never changes. So the slope of this line is just 0. The intercept is 5. So this is a special case of the straight line y equals mx plus b, where the slope is 0, so you just end up with y equals b, which in this case means y equals 5. All right, so it is, I guess you could think of it as a special case of the straight line function, but without a slope. All right, now the next one, the identity function, means that x and y are always equal to each other. All right, so by the way, just don't forget that when we write a function out like this, this is the same thing as y equals x, okay? Y equals f of x in all of these cases. So these mean the same thing, okay? So you can see y always equals x. They're mirror images of each other. So basically, when you draw this thing out, let's see what it looks like. Okay, so in other words, these are the points 0, 0, 1, 1, 2, 2, and you get the idea here that no matter what point we're looking at, they're both the same. All right, so if you're interested in knowing what the slope is, we could pick any two of these points. You might recall that the slope can be calculated as, of course, delta y over delta x. And that in turn can be calculated as, let's think of it as y2 minus y1 over x2 minus x1. So we can pick any two of these points at random. How about these two? And then if that's the case, delta is a shorthand. It's a Greek letter. It's used to represent change. So here, for example, it's the difference between these 2 points. So let's say I do pick these 2 points. I have 2, 2. Think of this as x1 and y1. And then I have 1, 1 for my second point. Think of this as x2 and y2. Now, by plugging those into this formula, you can see that I've got 1 minus 2 over, all right, 1 minus 2 over 1 minus 2. So I end up with minus 1 over minus 1, which is simply equal to 1. The intercept is 0. So basically, this is also a special case of the straight line formula, except that the slope is 1 and the intercept is 0, so we just end up with y equals x. Oh, by the way, I think I mentioned this last time. If you're having an issue visualizing what one of these functions look like, there's this really interesting website here called Symbolab. And the nice thing about Symbolab is it can do a lot of calculations for you, but it can also do graphs. Like if I wrote y equals x right here, it's going to come back and offer me the opportunity to create a graph. And it's just exactly what we did. Okay, so in a lot of cases, it may not be immediately obvious what these things look like. Now here it wasn't a problem, but in many of these cases we'll be looking at, the graphs are very hard to imagine. So this is a good way to at least see what's going on. Eventually you'd like to be able to do this yourself. But you know, in the short run, you know, when you're still learning about how these functions work, it's nice to have this tool available to you. So it's Symbolab. Let me write that down a little bigger. Now, I'm not getting a commission on this or anything. I stumbled onto it purely by accident. Oh, for God's sakes, let me make that a little bigger. There it is, Symbolab.com. That I recommend it very strongly. It's not even just for the graphs. It can also help you solve equations as well. It's very sophisticated. It goes up as high as pretty advanced calculus. So I would say, at least be aware that this website exists, because you'll get a lot of use out of it, especially in a class like this. Oh, I did. Yes. Thank you for recommending it. I'm definitely going to investigate that, because it seems to cover a lot of different areas that, not just obviously pre-calculus, but all the other topics. So I just barely had time to go find it, but I liked what I saw. So I'm definitely going to look into that. And what I like about it is that we could actually use it to practice without necessarily having it count as, like a quiz, for example. And so I think the more practice we can get, the better off we'll be. And so, although again, I just barely had time. Last week was the first week of school, and you can imagine how busy that was. But I'm glad that you recommended it, because I think I can put it to good use. And that includes this class as well. So I'll set it up. I have to learn how to use it, of course. I'll set it up so that everyone can practice with it, because I'm sure that will come in very handy. And so that's where we're going with that. It'll take a little longer for me to get it ready, but I definitely want to use it. So for everyone else, this is an online website where you can create math quizzes, and everybody can get their hands on it and get a lot more practice with these types of problems. It's sort of nice to know, because then I don't have to write all the questions myself, but I do have to know what questions are being asked. All right. So anyway, let's get back to this.
What website was it again? Sorry.
Oh, Delta Math.
Delta Math. Okay, cool.
Yes. Let me put that in here as well while we're discussing these great websites. It's like I don't know. There's like a free version of it that anyone can use. You may be able to go in there and do it yourself. I'm not sure. Like I said, I'm still learning it or learning about it. But at some point, I definitely feel like I'm going to set it up so that we can put it to good use, because there's no class where practice isn't helpful, but especially in math. Okay, it's important, very important to get as much practice as possible. Now, having said all that, by the way, we do have some problem sets of our own on Moodle. Let me just go point that out to you, that we'll be working on soon, not just yet, but soon. And these are not meant to be collected, but meant for us to work on together and make sure we understand what we're doing. So it's the same principle, but I think online is pretty cool, isn't it? It's kind of nice that you can type in your answers and get your solutions right away. So that's another reason why online is such a helpful way to learn, because you get feedback immediately. Okay. And plus, it's just fun. Let's face it. It's almost like a video game. Not really, but I mean, it has elements of a video game to it. So there they are. So we've got these 3 practice problems. They may not have been up there last week. And so basically, you'll see that this is just what we've been doing. Let me get this thing open. And so when we're ready, we're going to work on these together. And the whole point is just to get some practice. Here we go. So let's see what one of them looks like. Okay, so you can see in this practice problem set, we're basically learning how to evaluate functions, which we did last week, and getting more practice at it. Not terribly complicated, but it's a good starting point. And then the other 2, there's 3 altogether. So at some point, maybe as soon as next week, we'll start working on these before we start to forget what we're learning. And hopefully by that time, I'll let you know what's going on with the Delta Lab. All right. So like I said, especially your class that only meets once a week, the more time you can spend practicing, the better. Beautiful. All right. So yes, back to this. Now, the absolute value, you've all been, introduced to that somewhere along the way. And in fact, all it's really doing is saying, let's get rid of the sign. Okay. So no matter what the number is, let's say if x is -2, the absolute value of x is 2. If x is +2, the absolute value is also 2. And why do we have this function? Because for certain applications, we may have numbers that are negative, but the negatives are not useful information. We don't really need to deal with that. So we often will sort of ignore the negative sign, or else we'll use the absolute values because the magnitude is what we're really interested in. So what does that look like? All right, I lost my place here. Here we go. So this is what the graph actually looks like. And you can see that it is simply a big V because the left and the right-hand sides are mirror images of each other. Oh, and this is a typo, I just realized. All right, make a note of that. I have to fix that. What is that, slide 66? That should have the bars around it. That's f of x equals absolute x. Okay. Now, you can see that another interesting thing is that there's no value of x for which y can be negative. So the range of this function is 0 up to +infinity, which means that y, or f of x, can have any value from 0 up to infinity, but it can't be negative. The domain is just all the real numbers. Okay, there's no value of x that can't be substituted into this function, but the range is limited to the positive, or actually I shouldn't say positive. These are the so-called non-negative numbers. And all that means is that they're all either positive or 0. So non-negative simply means all the numbers that are either positive or 0. So the range of this function is what we call the non-negative numbers. Pretty interesting. All right. Oh, wait, hold on. Did that make you hungry? All right, now the quadratic function. Now this is something you've also been exposed to. Now, if you notice, we have 3 terms here. The only constraint on this one is that a can't be 0 because otherwise it's just going to reduce to a linear function. So in order for it to be a quadratic function, a has to be non-zero. The other 2 terms don't have to be, I mean, they can be 0, and this is still going to be quadratic. But quadratic simply means the order of the equation is 2. Now, what does that mean? The order of an equation is the highest exponent. So we say the order of the equation is 2 when we mean, what that means is the highest exponent is 2. So for a quadratic function, the order is 2. And that's what this name actually tells us. All right, now you know from experience, you probably remember solving these using the quadratic formula, okay, or factoring. But we do know that quadratic functions look typically like a big bowl. All right, the 2 cases you normally encounter would be maybe this one and this one. Okay, this depends, by the way, on the sign of a. So for this one, for example, we have x squared minus 2x minus 15. And if you're not sure what this looks like, you can take this over to Symbolab, but I've already got it right here. So there's no need for that. Although, you know what, let's do it anyway, just to get some practice with it so you can see how this website works. The one thing I noticed about it is that in order to get a result, and you know, just from fooling with it, if you just write x squared minus 2x minus 15, it will not understand what you want. So make sure that you start it out with y equals x squared. And here's the exponent box. Minus 2x minus 15. Now when you hit go, It'll give you a bunch of discussion down here. If you notice, for example, it's going to help us by telling us what the domain and the range are, which is nice if that's what you're looking for. It's going to tell you where this function intercepts the horizontal and vertical axes. The vertex, we'll discuss that later on in this chapter. But right now, we're only interested in the graph. So let's click on the graph button. And there it is. And it does look like kind of a big bowl. It's facing up because the coefficient of x squared is positive. If this was negative x squared, then the whole thing would be upside down. In fact, why don't we prove it right now? Let's change this to negative, and let's see what happens. Upside down, just as we predicted. And you see, this is another nice thing about having this tool. You can fiddle around with it and see what happens when you change these terms. You never know how much you might learn by being able to change it and see what happens as a result. Okay, so just remember, it faces up. If this x squared term is positive, it faces down if the term is negative. And this shape that we're looking at here, as you might recall, is referred to as a parabola. Okay, now this graph was done in Excel, so it looks a little different, but it is correct. The thing about Symbolab sometimes is that, like you can see, it can get a little, I don't know if we have any control over this, these axes. You see, it's trying to cover a lot of territory. It goes, you see how it's going all the way up to 30, whereas this one only goes up, well, all right, they're not that much different, are they? But oh, you know why it looks so much different? Because look on this, on the horizontal axis, it's going all the way up to 10 and negative 10, whereas this one only goes out to basically negative 5 and positive 5. So they look slightly different, but if you drew them all with the same axes, they would be exactly the same. I think you can zoom in on it if that's what you want. Yes, okay, that's what I figured. I think you can make the whole screen. Ooh, okay. I'm not sure if that's what I actually wanted, but anyway, so this is how it works. All right, and you can see, by the way, there's all this other stuff over here too. I'm not quite sure what they're offering us to do, but there's all kinds of fun stuff in here. Partial fractions, long division, the whole 9 yards. It's here somewhere. All right. Now, cubic function. So here the order of the equation is clearly 3. And all I mean by that is that the highest exponent is 3. And of course, we have to be aware, make sure that a is not equal to 0. Otherwise, it reduces to something simpler. Now, this kind of graph is very, very difficult to visualize. The shape can be very different depending on the magnitude of those coefficients as well as their signs. So this one is sort of like a, wow, I don't know how you would describe that one. Let's throw it into Symbolab for a second and just see what it looks like. Y equals x cubed plus 2x squared plus 5x minus 8. Okay, so we hit go, and it gives you all this information down here, and the domain and the range, for example. This one, the domain and the range cover the entire real number lines, as you can see. So there's nothing that's disallowed, basically, but let's take a look at the graph. Yeah, I mean, it's kind of like a big curvy thing. What I'd like to see is what happens if I change one of these signs. Let's try this and see what happens. Just out of curiosity. Ooh, boy, that is very different, isn't it? And what you notice here is that it crosses the axis in three different places. Now, I don't think I can write on here, sadly enough, but there's 3 points where this function crosses the horizontal axis. So we'll see more about that later on, but that's an important detail. But anyway, look at it, it's a cubic function, and as it showed you in the symbol lab, the domain and range are both the entire real number line. Okay, now the slope, by the way, we forgot to talk about this here. The slope depends on where you are on this curve. In other words, the slope changes. Unlike a straight line, the slope changes as we move throughout the function. So right about here, the slope is 0. How do you know? Because if you describe a tangent line to the curve at that point, the slope of that tangent line is 0 because it's flat. Remember, a horizontal line has a slope of 0. So if the tangent line is flat like this, the slope is 0, but up here, the slope is clearly positive. And over here, the slope is clearly negative. So with a function like this, which is nonlinear, because you have such a high order, the slope will not be constant throughout the function. And so in other words, the slopes are only constant for straight lines. For all these other functions we're looking at, the slopes are not going to be constants. Oh, one more detail here. If you notice, this curve only goes down so far, which means that the range is limited. Let's go back to this one real fast in Symbol Lab. Hold on a second. This one was y equals x squared minus 2x minus 15. So the range does not include all the real numbers. There's a minimum value that this function can have, and that is negative 16, it looks like. Okay, so they're writing it in interval notation, as if you can see that, negative 16 all the way up to positive infinity, because when we plug in negative 16 into this function, that's when it reaches its minimum value. In other words, that's when x equals 0. Right there. It's right about there. You can just about see it. Okay, but for this cubic function, it goes on forever. You can see that across the horizontal axis and across the vertical axis, it can take on any value in the real number line. Wow, the reciprocal function. Now remember, reciprocal means 1 over something. Okay, this, so for example, something like this. This is called a reciprocal because it's 1 over 2. Okay, and also as far as the terminology is concerned, just remember 1/2 is the inverse of 2. All right, you might remember that from somewhere along the way. 1/3 is the inverse of 3. And why is that? Because 1/2 times 2 equals 1. Okay, that's what the word actually means. Here, 1/3 times 3 equals 1, which is how we know that they're inverses of each other.
Hey, Professor.
Yes.
I was ask a question. I was just wondering, should we focus on memorizing like what each of these is, or should
Oh, no, I don't want, no, memorizing, no. But you do have to be familiar with certain terminology, just like in any discipline. It's great that you know a lot of these names and all, but it's more important to be able to do the problems, I think.
I was talking about like, should we focus on like memorizing what each of the graphs looks like for like,
No,
oh,
absolutely not. No, it's good. It's good if you remember them, but I wouldn't say go ahead and memorize them.
okay.
You know what I mean? Like, it's nice if you know that, for example, a quadratic function looks like this, but this is more just to gain insights into it. It's not something that you're being asked to memorize. Let's put it that way.
Okay.
It's
Is it
just
more
that
problem solving?
it kind of helps us to understand what this function is all about if we're looking at its graph.
Okay.
But if you needed, let's say, for example, this is an economics class and this represents your profit function, and you need to figure out how to produce the output that maximizes your profits. Well, this helps if you can see what this thing looks like, but ultimately what you're interested in is some solution or other. And that's really what the focus is on, is solving problems using these functions.
Okay, cool.
The graph is more like additional information, shall we say, that might give you some insights into how this function behaves.
Okay, cool. That's
Yeah,
pretty
I'm trying to de-emphasize memorizing things. It's just, any discipline has its own unique language that we have to get comfortable with, like this word inverse. Um, it's not that I'm going to say sit down with a dictionary and memorize all these mathematical terms, but like at some level, it's important that you know what they mean when you hear them at least. I know there's some classes where you spend half your time memorizing terminology, and it depends on what you're doing. Like in biology, you do have to learn an awful lot of key terms, don't you? But you don't have any equations, do you? Now here we're going to focus our attention on solving problems, not so much on learning terminology or and again, the graphs are really just a tool to help us understand what's going on behind the scenes. Like this one, for example, you can see that this is a very weird function. And so you can also see visually that it's not possible for x to be equal to 0. Why not? What's the problem?
have 1/0.
That's right. Are we ever allowed to divide by 0? No. In fact, I'm going to watch this. We all know what this means. When you have a big circle with a slash through it, it means no, don't do that. I don't remember when this kind of came into use, but they started out by having like pictures of cigarettes with a big slash through it when you weren't supposed to smoke. And also for crosswalks, like that was meant to indicate don't walk. But no, now actually, that reminds me, one of the videos that we're going to look at actually has a very interesting proof of why you may not divide by 0. Now, we know not to divide by 0, but we may not really understand why. So this video, which we'll see sometime today, will explain in pretty good detail without overwhelming you why this is the case. I think you'll find it extremely interesting. So something to look forward to, right? Imagine yourself being excited by the prospect of learning why you can't divide by 0. That's when you know you're a mathematician, when this really becomes an excitement in your to you. But it's important to understand how and why this is true, not just to say, well, don't do it. Understanding it is awfully important. Now, if you look at this graph, now keep in mind, I did this in Excel, which is not the best graphics package in the world. It should continue and get closer and closer, but never quite reach this vertical axis. Same thing here. It'll never quite touch the horizontal axis. Down here, we have these two are, by the way, mirror images of each other. And if you recall from somewhere in your travels, the XY coordinate system is broken up into what are called quadrants. This is the first quadrant, second, third, and fourth. And you can see the first and third quadrants are mirror images of each other. The second and the fourth are empty. Now, because these curves are reaching towards, but never quite reaching these axes, we say that the axes are, and you probably have heard this word before, asymptotes. Those are simply lines which a function approaches but never quite reaches. Okay, so let's go to Symbolab and take another look at this. I think the graph we can produce on Symbolab will be even a little more impressive looking. Let's do that. Let's take a look at it. And Yeah, look at that. It's kind of cool, isn't it? And you can see much more clearly here that that blue line, the two blue lines rather, will approach the axes but never quite reach them. So we call those lines asymptotes. That's the formal name for those lines, that it never reaches asymptotes. Now, another important note here is this: the domain consists of all the real numbers except what can't we ever substitute into here? All right, let's find out. So let's take a look. Oh, wait a minute, what happened? That's not the function I wanted. Do I have this thing open twice? That's weird. Maybe I do. All right, let's try that again. So if you look at down below, they'll point out to us quite correctly that the domain of this function is all numbers except for 0. Okay, we cannot substitute 0 into this function, as we've just seen, because that would lead to division by 0. So the domain can be written as negative infinity up to but not including 0, and 0 up to but not including infinity. So this is, remember, the union symbol, which means add these two sets together. And because we have parentheses here, this indicates that 0 is not included. Remember, if we want to include a number, we need a bracket. Here we have parentheses, which reminds us that the only thing that's missing here is the 0. On the other hand, for the range, there's the only value that is never going to come out of this is 0. Y will never be 0 in this case. So, and it's the same thing. You can see here the domain and the range are the same. 0 cannot go into this function, and it cannot come out of it. So the range is also negative infinity up to 0 union 0 up to positive infinity. Now, by the way, you don't have to, I mean, this is just one way of expressing the range. Another possibility, and you can see they're doing it in Symbolab, is they're just writing it like this. And this is a little bit more informal. F of x is strictly less than 0 or strictly greater than 0. Okay, up here, they're telling us that x, same thing. X is strictly less than 0 or strictly positive. In other words, it's strictly negative or strictly positive. One or the other, no zeros are allowed. Now, I don't know which one you prefer, but this book tends to use the interval notation, as it's called. All right, so what other goodies do we have here? There's just a few more. Now, like I said, there's plenty more that we could look at, but I think we want to focus on these basic ones. So how about, oh, and by the way, when there's a break in the curve like that, it's referred to as a discontinuity. Okay, the function is defined everywhere except at that one point. So, in fact, you may have seen this before. Let's say you had something like this. This is some function, y is f of x, but for some reason, when we reach 2, instead of what you would expect, let's say this is, suppose it would normally be 8, but instead there's one exception. This is, let's say, 12. This is referred to as a discontinuity. And I've been, when I was in high school, I remember they told us that the way to think about this is that when you draw this function, if you have to pick up your pen off the paper when you're drawing it, then you have a discontinuity. If you can draw it just continuously with your pen without picking it off the paper, then it is said to be continuous. That was kind of interesting, I thought. The way to think about it is whether or not you have to take your pen off the paper. Here you do, and so we say that we have a discontinuity. All right. So are all these good math memories flooding back into your memories? Is it all coming back to you in a big flood? Sure it is. Of course, you're stimulating parts of your brain that haven't been stimulated since you were in high school. And they like being stimulated. And all those memories come gushing back while you're doing this. Yes, it's coming back. Yes, it is. It's almost like all this fun stuff was like, it's like your memory is like an enormous closet. All that stuff is still there, but it's just a question of finding it underneath all the other stuff that you've saved in the meantime. It's just you're going back there and you're looking for something you haven't seen in years, but you know it's in there somewhere. All right, well, anyway, now the next one is an extension of this one. It's 1 over x squared. We call that the reciprocal squared function. Now, this one is a little different because all of a sudden, no matter what numbers we plug into this, y can never be negative. Okay, so it's going to change the shape in a very important way. All right, the reciprocal squared. So for example, if x is 3, this becomes 1/9. But if x is -3, it's also going to become 1/9 because 1 over -3 squared is 1 over 9. So that means that, well, all right, you'll see what it means in a second when you see the graph. Okay, hold on a second. That, oh my God, look at that. Now again, it's hard to see because it's Excel here, but this should go up and you notice it's never quite going to reach 1/9 is positive. It can't be negative. What we're saying here is that even if you plug negative numbers into this function, the result will always be positive because they're being squared. Okay, that's the idea here. Y has to be at least 0. Okay, so no value of x can cause this function to be negative. That's why we say, and we're going to see in a minute, that the domain is all values except for 0, because you may not substitute 0 into this function. Otherwise, you'll end up with division by 0, as we've seen already. But the range is actually going to be everything from 0 up to infinity. Y can never be 0. Okay, there's no value of x that will cause this function to be equal to 0. And you can see, because the curve never quite touches the horizontal axis, but it can be any positive value. Okay. Okay, now let's go back to Symbolab and see what Is has to say about all this. I'm going to change this to 1 over x squared. X squared. There we go. So first, let's look what it has to say about the domain and the range. And again, it's the same. For the domain, it's everything but 0. The range is, everything from 0 up. In other words, not including the 0. It's strictly greater than 0. And it also specifies here that the asymptotes are the horizontal and vertical axes, and that the function doesn't cross the x-axis. Okay, so let's look at the graph. That's the most fun part, isn't it? There it is, exactly. And you can see the left and the right-hand side are mirror images of each other, but the function never quite touches either the horizontal or the vertical axis, and so we call those asymptotes. Okay, I think that's all we need to say about this function. And of course, like before, there's a discontinuity because we know that x can never be 0. Well, asymptote just means the hands are the same. Yeah, technically, your body is symmetrical in certain key ways. Like the left-hand side and the right-hand side. Let's say this is you. If you drew a line down the middle, the right-hand side and the left-hand side are supposed to be the same, although maybe not exactly. But this is referred to as symmetry. All right, and that's what we do actually have here: symmetry on the left-hand side and the right-hand side. The asymptote just means that, like, let me show you an example that might help you with this. Imagine, you've probably heard of this paradox. You've got an arrow, and you're going to shoot it at a big target. And each second, it covers half the remaining distance. So let's say the distance is 1 to start out with. So in the first second, it goes 1/2 of the way. And then it goes half of the remaining distance and half again and half again. When will the arrow reach this target? The answer is never. Okay. And so we can think of this as like the limiting case of this, the path of this arrow. And so the same thing is happening here. They'll never quite reach these axes in the same way that this arrow will never quite reach the target. Now, in the limit, now in calculus, you'll run into this concept of the limit, which basically tells us where this function is converging towards, but not quite reaching. So we could say here that the limit as we move in this direction is 0, and in this direction is infinity. But we're not going to do that here, at least not yet. Okay, that will have to come later. All right, well, anyway, so the square root function. Now, this is something we may actually run into in applications. The thing about the square root is that it increases, but the rate at which it increases is slowing down. In other words, if you could imagine the slopes of this function, these tangent lines are getting flatter and flatter as we move to the right. So the function increases at a decreasing rate. And also, you notice there's some serious restrictions on the domain and the range. The domain is anything from 0 up to infinity, including 0. You may take the square root. By the way, hopefully you haven't forgotten that the square root of x is just x to the 1/2 power or x to the 0.5 power. They mean the same thing. You may not substitute a negative number in here. You cannot take the square root of a negative number, or at least if you do, it becomes imaginary, which is not something we're dealing with here, although we'll revisit that topic later on in the course. The domain, therefore, is everything from 0 up to infinity, including the 0, but the range is the same. The square root of 0 is 0. And after that, the value of the function is always positive. Okay, so this is our domain and range, and the slope steadily decreases. In other words, the curve gets flatter as x increases. All right, pretty cool, huh? So let's go to Symbolab and see a really nice picture of it. Let's see. Where are we? There we go. So let's try something different. Y equals square root of x. They do have a square root symbol here. And you can see that indeed the domain and the range. Now you notice how they use the square brackets. Let me make that bigger. They did use the square brackets. Oh, what happened? Oh, what did it do? I didn't ask for that. Yeah, anyway, so using interval notation, it's everything from 0, including 0, up to infinity. Here, you notice how they're also including the 0, but they're also up here writing it as simply all x's of 0 or greater, and down here, y's or f of x's that are either 0 or above. So let's look at the graph. And yeah, exactly. You can see now, of course, the actual function is much smoother than what we're seeing in Excel. But yeah, this is what it's looking like. It's all restricted to the first quadrant, and the slope is steadily decreasing. Okay, so I think there's one or two. Is there one more? Yeah. Oh, here we go. The cube root function. So don't forget, this actually is the same thing as x to the 1/3 power. We call that a cube root. For example, the cube root of 8 is 2 because 2 cubed is 8. Okay, so now that's going to be a weird function. Now, here's an interesting detail here. Let me just point this out to you. Okay, so let me just make up a little list here for a second. X to the 1/2, which is, of course, the square root of x, x to the 1/4, which, by the way, this is often referred to as the fourth root. X to the 1/6 is called the sixth root, et cetera, et cetera. Over here, I'll have x to the 1/3, x to the 1/5. This first one is obviously the square root, but you could also call it the second root if you wanted to. Over here, we have the cube root. This one is the fifth root. And of course, you know what's coming next, the seventh root. These are collectively known as the even roots for obvious reasons, because these are all even numbers. And up here we have the odd roots. So we already know not to take the square root of a negative number, but the same thing holds for all of the even roots. We cannot take an even root of a negative number. This applies to all of them. Or if we do, we'll get an imaginary number. Let's put it that way. Okay. Over here, though, it's the opposite. We can take an odd root of a negative number. Okay, I'll prove it to you right now. What happens if I try to take the cube root of -8? Okay, well, let's see. It's -2. Why? Because -2 cubed is -8. So you can apply the odd roots to negative numbers, but not to the even, not over here with the even roots. Okay, so just be aware of that. Odd roots, yes, negatives are okay. Even roots, no. All right, so with all that being said, let's see what this thing looks like. All right, so all of these are odd, these are even. Just remember the key to the whole thing, Odd roots can be applied to negatives, even roots cannot. So this is what it looks like in Excel, and it's kind of clunky looking, but it gives us an important insight. Because it's an odd root, though, there's no restrictions on the domain or the range. So the domain is just the entire real number line. And so is the range. It can take on negative numbers. And as usual, I mean, you can see the slope is changing. The slope is actually interesting because it's kind of flat, and then it starts to get steeper, and then it gets flat again up here. So the slope increases and then decreases. So for a while it's increasing, but then it hits some critical point, and then it starts to fall back down again. And we'll discuss that later on, what that means. But yeah, all right, let's do this. Let's go back to Symbolab, and let's see what cool graph it can generate for us. All right, here we go. So it does have, look at this box. This is meant to indicate you can take any root you want. So put x here and 3. But I do want to point out that you could have just as easily written it as x to the 1/3 power. All right, so just as we predicted, you can see, oh God, come on. There we go. The domain and the range are both the entire real number line. All right. And when we graph it, wow, look at that. How cool is that? Yep, and you can see there's no values that we're not allowed to use. All right, so that's fine. So that was kind of fun. Graphs were always fun. You know what might be interesting? Let's try this. Let's just see what would happen if we do this with a negative x. Oh, you see, we basically flipped it upside down, but it still has that same basic shape. How do you like that? All right, so let's get back to the slides. And now what we're going to do is introduce techniques for finding. Now, finding the domain is maybe not necessarily the easiest thing in the world. Here we've been able to do it with these very basic functions, but sometimes it can be a real challenge. And so there's certain techniques that we can learn that helps us identify them when we have unusual cases or very complicated cases. And of course, don't forget what the domain actually means. It simply means all the values that x can attain or be substituted into this function. All right, let me put this in here. Just as a reminder, the domain represents all values of x that can be substituted into a function. Normally, that would be all real numbers, but not always. We saw there's several important exceptions. So first things first, if our substitution causes a function to become undefined, that means we have to leave it out. And of course, that often means division by 0. But it can also mean negative square roots. So in other words, any value of x that causes either division by 0 or taking the square root of a negative number means we have to exclude that from the domain. And that's usually where the problems are. Division by 0, taking the square root of a negative number. All right. So yeah, I mean, you're looking at the input values, looking for any possible restrictions, leaving them out, and then you're writing out the domain as an interval. Now, It's not the only way to write a domain as we've seen, but I think it's maybe the most consistent way of doing it. All right, so here's a simple example. I've got coming up a quadratic function here. Now, you know, with quadratic functions, any value of x can be substituted into it, but there may be a restriction on how many values of y there can be. All right, let's look at our first case. This one. Now, here's where having a graph could be very helpful. I'm going to go back to Symbolab, and we're going to see what this thing looks like. X squared minus 5. All right, so what I really want you to see, now it's going to tell us right here, it's going to spoil the fun by telling us that the domain is all real numbers, but the range is everything from -5 up to infinity. So we're going to see why. Why is it the case that y can never assume a value less than -5? Let's look at the picture. Oh, there it is. And you can see the function starts at the point 0, -5. It's never, there is no value of x for which this function can take on a value below -5. So the domain starts here and goes, the range starts here and works its way all the way up to positive infinity. Whereas the domain is the entire real number line. All the values of x are covered. It may not look like it because it's so steep, but yes, this does go up forever. So the domain is the entire real number line, but the range begins here at 0, -5, and we work our way up to positive infinity. So in other words, y is -5 and up, including the -5. So that means we need, when we write this, we need to make sure, whoops, oh, you know what I just realized? The question only was about the range, the domain, not the range, but still it's good to know how to do the range. But I just want to point out that the range hold on, is everything from, wait, we need to include that, -5 up to infinity. But I just realized that the question was what is the domain? The domain is simply all the real numbers. And again, that's because there's no value of x that could be plugged into this formula and either lead to division by 0 or the taking of a negative square root. Now, with this next case, that's not the case, is it? What's going on here? There's a value of x which could cause problems for us. What value is that?
0.
0, exactly. So it should be pretty clear that the domain will include all real numbers except 0. So we can write it like this. And so the union again means we're combining the two sets. But if you notice, because these are parentheses rather than brackets, 0 is not included. Okay. And we've already seen this graph, but we may as well just plot it out again. Since this is here, let's plot it. And you can see it'll tell you itself that the domain is all values except for 0. And it turns out the same thing is actually true of y. Y cannot be 0, so the domain, the range rather, is everything from -infinity up to 0 and 0 up to infinity, but not 0 itself. So here we go, let's graph it. There we go. This looks familiar, right? We've seen this one before. So you can see, and then we have the asymptotes, which they do mention in here somewhere. Yeah, look at that. X equals 0 is the vertical intercept, by the way, and y equals 0 is the horizontal axis. So anyway, that's that. Now, how about, what about this one? What value of x could potentially cause problems here?
5.
5, exactly. No 5s are allowed in this function. You cannot let it 5, precisely. So I'll tell you what, now that should be clear from here, but again, when we look at a graph of it, I think it'll be even more clear why this is happening. Oh, well, they wouldn't cancel out. You have division by 0, and all that matters is that you have division. If you plug 5 in here, you're going to get 10 over 0. And so that's exactly what we want to avoid, because we may not have 0 in the denominator. All right, that's the point of this. There's no canceling can happen here, but you will end up with 0 in the denominator. All right, not good. Yes, okay, great. And don't worry, we're going to see that video pretty soon where it really explains this. Okay, why? No, what I mean is it explains why we can't divide by 0. Okay, but now let's take a look at the picture so you can see exactly why we may not have x equal 5. So our ratio is x plus 5 over x minus 5. Why did it do that? I noticed that sometimes it has a mind of its own. It's like it's saying, "What? Oh, did you mean this?" And that's pretty uncool, I think. All right, let's take a look at that old graph. And wow, look at that. Now you see it's very much like 1 over x, except the asymptotes are different. It has 2 asymptotes, as a matter of fact. And so here, this should be where x equals 5. We may not have a value of x equal to 5, but it also turns out y itself can't be equal to 1. Huh, how do you like that? Y can never be 1. So the range is restricted to all values except for 1. That would be interesting to prove. See, now that would be hard to figure out by looking at that function. It's very obvious that the domain does not include 5, but I never would have guessed that the range excludes 1. And it just means there's no value of this function where y equals 1. I think what you would have had to do, I get it now. You'd have to use the concept of limits to prove it, which we will not be able to do until the end of the course. But yeah, I can see it now. How do you like that? Okay. So how about this one? Oh, now you can see we're asking for trouble. What value of x, or values, I should say, would be disallowed in this case? That's right, or 3 itself, too, for that matter. So the domain is everything from positive 3 up to infinity, but not including 3. Oh, actually, no, I'm sorry. You were right. I was wrong. 3 is okay here because that would just give us a 0. So let me fix that. We can include 3, but nothing below that will be allowed because that would lead to a negative number here. All right, so let's go back here and see what it looks like. All right. So what does that graph look like? Now you see it's exactly like the square root of x, except that it breaks through the horizontal axis where x equals 3 instead of 0. It's as if we shifted it over to the right by 3. How do you like that? But yes, and you can plainly see that x is never going to be less than 3. And in addition to that, y will never be negative. Okay, so x can be 3, but not less than 3, as we saw. And in addition, the range is restricted to everything from 0 up to positive infinity. I like that. But it's the same basic shape as square root of x. It's just that it's been shifted over by 3, which is, by the way, a topic we'll be looking at in the second half of this chapter. All right, let's see, what's next? Oh, so here what I've done is I've gone through and summarized the domains and ranges of our basic functions that we've been looking at. So for example, here, with a constant function, the range is very interesting. It can only be one constant. So if, for example, remember we had the case of f of x equals 5, y can only be 5. So the range is restricted to 5. We don't even really need to write it as an interval. It's just 5. No matter what x is, y is 5. Well, that makes things simpler, don't you think? Okay, so how about the straight line function, or the identity function? Yeah, here there's no issues anywhere. Remember, that just looks like this. So you can see just by looking at it, there's no restrictions on either the x's or the y's. So their domain and range is just the real number line in both directions. Beautiful. All right, how about the next one? Oh, absolute value. Remember this one? It's a big V. Well, all right. I didn't get it just right. They're supposed to have the same slope on either side, which is 1, by the way. Now that's a little bit better. And now here, the only constraint is that the y can never be negative. So the range is 0 up to positive infinity, including 0. And you can tell just by looking at it, there's no y values down here. Okay, now for the quadratic function, I just realized that I have to fix this a little. Technically, the range can be anything, but we can see that depending on this value of a, b, and c, there may be constraints on the range in the sense that there's some minimum value for this function. So this isn't technically correct for all of them, all parabolas. So I'll fix this. Let me make a note of this. This is a special case. It may be covering the entire real number line, but there typically is a minimum point, so I'll have to fix that one. This is slide 98. But that depends on what those particular numbers look like. All right, because we saw before a parabola that started at -5 or whatever it was. And so the range in general will not necessarily be the entire real number line. All those values are possible, but each case is different. So I'm going to have to tidy that one up a little bit, and I'll post it later on when it's been fixed. Same, no, here that isn't a problem because these cubic functions typically go all the way to positive and negative infinity on both axes. Yeah, there's nothing, that's because there's no constraint on cubed functions. They can be both negative and positive. So we saw a couple of these earlier. One of them looked like this. And one of them was more like, yeah, it was kind of like this. But there's no limit to how far it can go up on either axis. So this is fine. Now, what about the inverse? Now, this one we've already discussed at great length. This is the one that looks like this. We have two asymptotes. Let's try that again. And so because of that, hold on. All right, that'll have to do. You remember this one. Both the horizontal and the vertical axes are asymptotes. So we can't have, x cannot be 0 and y cannot be 0. That's why the domain and the range look like this. They both exclude the possibility of 0, but all other values are possible. All right, so how about 1 over x squared? It was similar, but not quite, because here we're restricted, the y's are restricted to positive values. Okay, that was this case. And so you can see that, yes, once again, x cannot be negative. And it can't be 0, rather. And y cannot be 0 or negative. That's why the range looks like that. All right. And I think, we already understand why this is the case. So let's jump ahead to the square root of x. And that would be this case. So here we do start at 0. So both x and y can have a 0. You can see the bracket means we're including zeros, but neither one of them can be negative. In other words, we're restricted to the first quadrant. So neither x nor y can be negative. Okay. And then this one was a little bizarre. But you can see that in this case, there's no restrictions on x or y. Okay, they can go out all the way across both axes. There's nothing to stop us from doing that. All right. So are we getting pretty good at this? All right. So let's now, oh, here's another example. Now, imagine yourself on a test. This could be a typical question. Why don't you take out a piece of paper if you don't already have one and figure out what are the domain and range of this function? I'll give you a minute. All right, what did we get? Well, first, let's go back to Symbolab and see what it looks like. Let's see, I need a ratio. 5 over x, whoops, x plus 2. Oh boy, look at that. Something's not allowed here. So it looks like, is that right? Oh, well, wait a minute. Now, what did they do here? Oh, see, this is very confusing what they've done. It looks like the black is the vertical axis. The red, this red is both the asymptote and the horizontal axis. This red line is x equals -2. Ah, okay. I was confused for a second by what they did, but you can see that the only value that we're not allowed to have for x is -2. But when it comes to y, there's no value except 0. Okay, so 0 can't happen either. All right, so this is how it works. So x cannot be -2. Y cannot be 0. Now, why can't y be 0? Because we have a constant in the numerator. In order for y to be 0, we must have a 0 in the numerator. Okay, so that's really the holdup. 0 cannot be in the numerator, and that means no. We can't have 0 in the denominator no matter what, but without the possibility of 0 in the numerator, that rules out the possibility that y can ever be 0. And so the range and the domain are easy to write. So this is our domain. And remember, how to interpret this, this means all values but -2. And the range would be, on the next slide, I'll just copy it here for you. all values but 0. And that's, and you can see again by this graph, although it's a little strange the way they wrote it, that's, again, what they did was they put it, this is x equals -2. So we've got, this. All right, well, that was kind of challenging, but I think you can see how the picture can really be very helpful. Okay, all right, so this piecewise functions, these are strange. I'm not even sure Symbolab can graph these guys. These are kind of weird because what's happening is that the function essentially has two sections to it that are very different from each other. So, oh my God, it's already 9:30. All right, now, as you know, this is like a marathon, this class. So what we will need to do, in my opinion, is basically have 2 breaks before we pass out. So we'll have one now, and then we'll have one a little later. But when we get back, we'll cover a couple more topics, and then I think I want to show you some of these videos that I've been talking about because I think you'll really find them very interesting. All right, so let's stop here for a bit. We'll have our first break, recuperate a little bit, and when we get back, we'll carry on a little bit further. But then I want to show you at least 2 very cool videos that I think you'll really have a lot of fun with, but learn a lot, of course. That's the most important thing. Okay, so let's stop right here, and I'll see you in a bit. All right, here we go. So, all right, piecewise functions. Let me just quickly see if this is doable in symbol land. I'm not so sure. What's happening here, though, is that the function is broken up into two pieces. So while x is negative, the function is equal to 3x. When it gets into positive territory, though, it's now equal to x squared. So it's a very strange little function. Now, I managed to do it here in Excel, but it's sort of hard to really appreciate what it looks like here. It's just basically a straight line up until we get to the 0, and then suddenly it becomes a curve. So because it has two distinct regions to it, or two distinct shapes, the proper name for this in math is piecewise function. Basically, it's like two functions patched together into one big one. Now, I don't know if it's possible to do that here. Maybe I'll have to look into that. It would be nice, but I guess, all right, we'll worry about that later. This is roughly what it looks like. So just in general, you don't run into these very often, but you do sometimes see them. So it's important to be aware of what they're supposed to look like and what they actually mean. Now, rate of change, this is something you may have run into in high school physics. The average rate of change for a variable over a given interval of time is defined as the change in the output divided by the change in the input. And so, for example, if you're thinking of a car driving along the highway, or maybe if you're thinking about how much our profits change as we produce more and more of a product, that's when this type of function becomes, or this concept becomes very important. So here's an example. What if we have, now, by the way, you recognize this as simply the slope of a function, and it can be written in a couple of equivalent ways. We can have delta y over delta x. We can have y2 minus y1 over x2 minus x1. This assumes that we're looking at two different points on, let's say, whatever this function happens to be. It doesn't have to be a straight line either. It could be anything, really. So you would have 2 points. We could call this one x2 comma y2, and this could be x1 comma y1. And so the numerator here is the difference between the two y's, and the denominator is the difference between the two x's. So remember, delta means change, and when we say change, we simply mean the difference between the two. And of course, remember that f of x and y represent the same thing, so we can write it as f of x2 minus f of x1 if we want to. All right, here we go. So here's an example of when this might be useful. Let's see this one. What if the price of gas in 2009 was $3.29 and it is, well, in 2019 it was $3.49? What is the average rate of change over this period? All right, so if you can imagine, the gas price started at $3.29 and it slowly increased to $3.49 over a period of 10 years. So we're trying to find out basically on average, how much did it go up each year? That's really what this is all about. Now, of course, it's possible that it went directly from one to the other, but we want to figure out what the average increase is per year over this 10-year period. All right, so in this case, the first one, the earlier one chronologically, the X's are the years. Yes, that's exactly right. The X's are the years, and the Y's are the gas prices. So in other words, you could think of this as X1 is 2009, X2 is 2019, Y1 is 329, and Y2 is 349. So basically, all we're interested in is the change in one variable with respect to the other variables. So if you plug it in like this, the difference in the 2 years is 10. Sorry, the prices. Sorry, it's 349 minus 329. The years are 2019 minus 2009. So in other words, the price went up 20 cents over a period of 10 years, which means an average of 2 cents per year. That's what it means. So in other words, if it took 10 years to go up 20 cents, that translates into an average of 2 cents per year. And that's really all there is to it. Okay. All right, does everyone get that? Exactly. Now, the next example involves stocks, which I think you'll find interesting. It involves a very important idea from finance, and that is, you'll see this in a second. I've got a chart with prices, and let's look at it. Now, you'll notice at the top here, S&P 500. Does anyone know what that is? Well, first of all, it stands for Standard and Poor's 500. And it's an index created from the 500 largest US stocks. So in other words, they take a very complicated formula and then they take all the prices of these stocks and they turn it into a single number, which is very, very widely watched on Wall Street, by the way. If this number is going up, that means the economy is doing well, the market's doing well, everybody's happy. So imagine if you were to go and look up the actual values at the end of each of these 5 years, and this is what you came up with. And you see that we started out in 2015 with just a hair under 2,000. And by the time 2019 was over, it was all the way up to 2704.10. So you can probably see where this is going. We want to figure out, on average, how much does the S&P 500 go up during this period. So that means that if you're going to look at, oh, okay, so for whatever, the question is 2016 and 19, all right, whatever. You could do this for any 2 years you want. So these are the years. So again, X's are years. But if you look at the chart, the price in 2019 was 2704.10, and the price in 2016 was 1940.24. So in our formula, this right here, exactly, this is the 2019 price. This is the 2016 price. So basically, over a period of 3 years, the index went up by about 763 points. And so that works out to an average of 254.16 points per year. And so this could come in handy if you're trying to plan, your investment strategy, or if you want to understand if you'll ever have enough money to retire. This could be very useful information. And you can probably think of a lot of examples of this. Just as long as there's two variables that are changing, we can use this formula to help us understand the average change over a given time interval. All right. Here we go. Now this is different. This is a quadratic function. We don't have any numbers. We have to provide them ourselves. In other words, you have to find out, for example, let's call this x1, and let's call this x2. F of x1 is what the value of this function is when x equals 3. And how do you figure that out? You have to substitute the 3 into this function, and come up with this number yourself. And then the same thing with x2, you have to solve this yourself by evaluating it when x equals 6. Okay, so there's an extra layer of complexity here. But again, it's not hard. All you have to do is replace each x with 3 in the first case, and each x is replaced with 6 in the second case. No, we're not going to need to factor anything. We're just solving it directly. So you'll see. Hold on. So let's first do this. When x equals 3, well, actually, they're both on the same slides. All right, here we go. So here's the original function. So if we think of this as x1, this is x2. This is now f of x1. We plug in the 3 and we end up with 5. This is f of x2, which, now remember, you see here we plugged in 6 for x and we ended up with 23. So the average rate of change, and in this case, we're going to use the following notation. We'll have in the numerator 23 minus 5. Down here we have the actual x's, 6 minus 3, 18 over 3, which is 6. And that's all you have to do. But you notice how this time we had to figure out for ourselves the values of the f of x's or y's as you want to look at it. Other than that, it's exactly the same procedure. So basically, if you can visualize this parabola, it's going to look something like this. And so we're looking at, let's see now, let's say x is 3 here, and x is 5 here. Oh, I didn't do a very good job here. Hold on. So yeah, in other words, we're essentially looking for the rate of change over this interval. How quickly is this function increasing? Whoops, this is 6, between 3 and 6. So when x was 3, the function was equal to 5. And when x was 6, the function was equal to 23. So essentially what we're doing is calculating the slope of this function between these 2 points. That's where the formula actually is coming from. It's just the slope itself.
Can I ask a question about that?
Yes, go ahead.
It just like seems to me that if I like look at that, my like immediate reaction was like, oh, the slope is always changing at like every moment.
It is.
So then like just how I feel like a slope of 6, I feel like it would be 6 at like one very tiny point on that.
Yes, that's true. You're essentially averaging out the slopes across this entire curve. In fact, this is going to be something that becomes important in calculus. As you keep getting closer and closer to each other, you'll eventually find the slope at a single point, and that will be referred to as the derivative of the function at that point. But here we're looking at a large interval, so this is only an approximation, and you're quite right about that, because you'll notice if I could draw it a little bit better, you're basically creating what's called a secant line here, because it cuts through the function twice. And so the slopes themselves, as you know, at each point in this curve, they're slightly different. So this is essentially an average of all the slopes over that interval.
Okay, that really makes sense.
Right.
Thanks.
So just think of it as an average of all the slopes in here.
Thanks.
All right. So anyway, what else do we have? Oh, changes in a function. We can use, we're going to try to figure out where a function is increasing or decreasing. Now, all right, let's throw this one into Symbolab real fast. Our old friend Symbolab, it's now our best friend, isn't it? Because it's so convenient. y equals x cubed minus 12. All right, let's get that. X cubed minus 12. And by the way, don't forget, now this is something I've figured out the hard way. If I try to graph it right now, it won't understand. You have to hit the go button before you graph anything. I guess it stores it in its memory or something. So look at this thing. Well, that's a strange function. But it looks like there's no point where it's actually decreasing. It looks like it's increasing throughout, but not always at the same rate. Okay, in fact, there's a point here where it's actually kind of flat. So let's see, but the slope never actually becomes negative. So let's see what happens here. Yeah, see, there's the thing. The Excel doesn't always, let's look at this thing again. Oh, no wonder. I mistyped it. Oh, I was going to say something's wrong here. This is 12x. Okay, well, that explains everything. Because I originally meant in this example for there to be regions where it is decreasing, and I was a little concerned there, but that's because it wasn't the proper function. Now we're getting somewhere. So you can see that up to this point here, the function is increasing, and then in this range it's decreasing, and then it's increasing again. This is pretty typical behavior for a cubic function. And you notice again, it crosses through the horizontal axis at 3 different points because it's a cubic function, whereas a parabola only cuts through twice. So this is roughly what it looks like over a smaller interval. So we're trying to figure out where does it, let's see. And by the way, one thing you do want to do here is it helps a lot to identify any points where the slope is 0. So wherever the tangent line is flat, that means the slope is 0 because the slope is delta y over delta x, and a flat curve means that delta y is 0. And this is a point where the function is changing from increasing to decreasing, or the opposite. So here it's going up, here it's decreasing, and you can tell because the slopes are all negative in this range. But then all of a sudden it bottoms out again and it starts increasing again. So how do we identify the ranges within which this function is either increasing or decreasing? All right, so let's see how that works. So yes, you can see from this graph, this is the point -2, 0. This is the point 2, 0. No, wait, that's not right. What did I do? Sorry about that. No, that's not right. It looks like this is a 20 right here. Hold on a second. When x is -2, we have -2 cubed minus 12, -2. That's going to be -8 plus 24, 16. Okay, so this is 2, 16. What do we have down here? F of 2 is 2 cubed minus 12 times 2, which is 8 minus 24. So this is -16. It's hard to tell because these numbers are so large here. So this is 2, 2, 16. Here we have negative. Those are the 2 points at which the function either reaches a maximum or a minimum value. Everywhere else, it's either increasing or decreasing. Okay, so the question is, where is it increasing and where is it decreasing? Well, you know what? We can tell, there's a way we can tell which is which. And by the way, because there's more than one place where this happens, the formal terminology here is this. Whoops. because the function will continue to rise and fall, we call this point, this is called a relative maximum. Why do we call it that? Because this is not the largest value of the function. That would be up here somewhere. But within this immediate area, there are no other values that are any larger. This is where the function gets very large, within this immediate area. So it's called a relative maximum. It's not, to distinguish it from what's called an absolute maximum or a global maximum, which is the largest value of the entire function. And for similar reasons, this is called a relative minimum. It's not the absolute minimum, that would be down here somewhere. But within this immediate area, it's the smallest that the function will get. In other words, y will never fall below negative 16 in this immediate area. So we call it a relative minimum. So how can we tell with this information where the function is increasing and decreasing? Good question. Well, let's find out. There's different ways of going about this. All right, let's see. What do we need to know? What we can try is this. We can evaluate the function at points just below or and just above that point. So actually, let me draw another picture of this to make it more clear, because my graph is getting a little crowded here. All right, let's try this. All right, I'm going to try to draw this again in such a way that we can actually see this a little more clearly. So remember, the function itself is f of x equals x cubed minus 12x. So we've already identified the point negative 216 as a relative maximum. Now you notice the way it looks, it's like the top of a mountain here. So what I need to know is what's happening to the function just before and just after. So let's say I try to evaluate it at negative 3. And I evaluate it again at negative 1. The fact that it's a maximum, relative maximum, means that on either side of this point, the function's value should be smaller than 16. Okay, so in other words, f of negative 3 is negative 3 cubed minus 12 times negative 3. So we have negative 27 plus 36, which is 9. And 9 is in fact smaller than 16. Now let's try that again for negative 1. That's going to give us negative 1 cubed minus 12 negative 1. 1 plus 12 is 13. Again, 13 is less than 16. So therefore, without just knowing these 3 points, we know that this must be a relative maximum because the points on either side of it have smaller values of y. So this must be the top of a mountain. It's a relative maximum. And that also implies that everywhere before this point, the function is increasing up to there. And then from that point on, it must be decreasing until it reaches the next relative maximum or minimum. Okay, so in this immediate vicinity, the function goes from increasing, hits its peak, and then it starts to turn down again. All right, well, then you can probably guess what's coming next. We're going to do the opposite with the relative minimum. All right, so let's go take a look at the relative minimum and see what happens. So it looks something like this. And we discovered that, right, here's our point. So I'd like to evaluate, and it's the bottom of it. Well, I guess you could think of it as the bottom of a valley. I want to evaluate it at two other points, just to the left and just to the right of it. And I want to make sure, and you can see in either case, the value of y should be greater than negative 16. If so, this is indeed a relative minimum. So remember, the function is f equals x cubed minus 12x. So f of 1 is 1 cubed minus 12 times 1, 1 minus 12, negative 11. And of course, negative 11 is larger than negative 16. Now let's do the same thing for 3. 3 cubed minus 12 times 3, 27 minus 36, negative 9, which is again larger than negative 16. So we've been able to prove that this is not only a relative minimum, but that the function must be decreasing as we move in this direction, and it must be increasing in this direction. And so that's what we were looking for. Now, when we get into the last chapters of the book, we'll have a more formal test for this. But here, this is enough to show when we found the top of a mountain, so to speak, which is a relative maximum, and the bottom of a valley, which is the relative minimum. And that identifies the regions within which the function is increasing and decreasing. Now, that was a lot. I know that was a lot to take in. We're going to go through these again. Don't worry. We've got plenty of practice problems. And also this delta math thing, I'm going to set it up pretty soon. And then we should be able to use it to our heart's content, I hope. I just have to learn how to use the thing. But don't you worry, you'll benefit enormously from having access to constant practice here. All right. Now, let's see. I forgot what comes next. Oh, one more thing. I just want to point out, this is just terminology. First of all, these are Latin words. So this is what you run into. The plural of maximum is actually maxima. And the plural of minimum is minima. All right, just remember that. And both of these are collectively known as extrema. So we have extremum becomes extrema, meaning that it could be either a maximum or a minimum. So extrema could be either. Okay, just want to point that out. But this word extrema means it could be either a maxima or a minima. All right. All right, so let's see what came next. Oh, no, this can wait. All right, this is a completely separate topic. This is interesting, but we can do this. I think it's time. I think we've earned a couple of fun videos, all right? So what I'm going to do now, this is something where we have to be very careful. Because these videos are copyrighted, in principle at least, what I'm going to do is when we're watching these, I'm going to stop the screen sharing. In other words, I'm going to pause the recording so that if you watch this video later on, you will not see the videos, okay? Because it could potentially lead to, let's say, legal problems. Not necessarily, but it's a risk. So we're going to stop the video. Now, if you want to watch the videos again, I will post the links on Moodle. But right now, what I'm going to do instead is I'm going to put it in the chat room for you so that you can find it. And then you can watch it on your computer. I'll watch it on mine. But the recording will not be going on while this is happening. So again, if you watch the tape or the video later on, you will not see these videos. It's just a precaution. Whenever it comes, anything legal, you always have to watch out what you're doing. It's very sad, but it's very true. All right, so these are videos I actually found for another class. I put together a nice little list of the coolest videos. Oh, you'll see what I mean when you get to these. The first one is a history of zero. And then we'll be able to look at our discussion about why can't we divide by zero. That's really the one that I want to focus on, but we're going to watch the history of zero first just because it's interesting. And this is it. And so when you get it, get the link, I'd like you to watch the video and then we'll talk about it if you want to. All right, so there it is. You should have it right in your chat box. And so why don't we start by watching this? First, I'm going to pause the screen and then we can start. Yeah, you know what? We found from past experience that the sound often doesn't work properly when doing that. Um, Yeah, we always had trouble with the sound, even when we were recording it. So I found from experience it's easier to let everyone watch it on their own screens, just because there's no guarantee that you'll be able to hear what's on my computer. I don't know why that's a problem, but it does seem to be. Um, so that's the solution I came up with, and then well, it turned out YouTube doesn't appreciate it if I record the video. So I think this is really the only option that we have right now. Anyway, so that I think you'll agree was kind of a fun little introduction to the topic of zero. It's the history of math is always far more interesting maybe than people generally realize. I mean, these ideas had to be developed somewhere along the way, and they came about from practical necessity usually. But and as you can see, it took a very, very long time for all the numbers that we have to be developed. It literally took centuries. And then it took a while to come up with ideas like negative numbers and fractions and all the rest, because there was no practical need for them in the early days when we were basically all doing agriculture for a living. And so, negative numbers would have made no sense. But that's right. But yeah, as time went by, obviously it became clear that we needed more complex number systems to take into account different kinds of situations that could arise. But zero, and like they said in the video, there's a lot of resistance in Western Europe to the concept of zero. In fact, if you remember when you were learning Roman numerals at whatever grade it was, the one thing that was missing from the Roman numeral system was zero. There was no such thing as zero in the Roman numeral system. And that's one of the reasons why the West eventually stopped using it. There's other reasons too, but that was one of the important ones. There wasn't a zero. And we know that we need zero for a system to work properly. Anyway, now the next video is the one that I really wanted you to pay close attention to. They're going to prove to you in a very interesting way why we're not allowed to divide by zero. Okay, now everyone's been told since they were little kids, don't divide by zero, but now you're going to have more insight, I think, into exactly why this is the case. And I think you'll see that it makes a lot of sense. But anyway, it is a little bit more conceptual, but you'll see. I think you'll really like it. So let me go get the link. Why can't we divide by zero? All right, here we go. So I'm going to post it in the chat room. And where did it go? Here, I was staring right at it. All right, here it is. Why can't we divide by zero? So let's check this out. Well, is everyone done watching it?
Not quite. I have like 1 minute left.
Oh, okay, go ahead. Carry on. Oh, we have to save Riemann sphere for some other time. That because that involves the imaginary numbers. But we do have a video ready to roll with that one. We just have to hang on to it for a little bit longer. So yes, what they're implying here is that if we allowed division by 0, then all of the integers would be, all the numbers, real numbers, would all be equal to each other and equal to 0, which means we are left with nothing. So it's a very strange thing to think about, but division by 0 would essentially, it would be kind of like destroying the universe in a sense, because then all of math would mean nothing if all the numbers are equal to each other. So yes, that is one thing that is definitely not allowed. All right, now.
I have one quick question.
Yes, go ahead.
So, like, I think I get the overall concept for sure, but while I was watching the video, one question popped into mind where they were like 1 times 0 is 0.
Right.
And that makes sense to me, but I was thinking that too, like, what would also make sense to me is like if you already have 1 and then you don't multiply it, wouldn't you just still have 1?
Sure. I mean, if you don't multiply, it's 1 stays at 1. But because we need to multiply, because remember what we're trying to do, multiplication is the inverse of division. And so if you can divide by 0, you have to be able to multiply by an inverse. And so that's the sticking point, because the inverse, is he's saying in the video, doesn't exist. Because of the rules of math, there cannot be any such inverse when it involves 0.
Mm-hmm.
So anyway, so well, I mean, it was an interesting look at the reasoning behind this. So now we gain some insights into the history of when 0 was developed, and we also now have some understanding about why we can't divide by 0. Now, I have a couple of others here that I think we should look at today, just because I guess maybe we're in the right frame of mind for studying math history. The next video explains, it talks about irrational numbers. So I just want to quickly remind you, a number is said to be rational if it can be expressed as the ratio of 2 integers. Like, let me write that down in my PowerPoint slides here. Just as a quick review, in case you've forgotten, because this next video will explain some important results from the history of math. A rational number is a number that can be expressed as a ratio of 2 integers. For example, 19.4 could be written as 194 over 100. Therefore, it must be a rational number. But on the other hand, how about pi? All right, our old friend pi from high school. We know, or at least, well, you've been told that pi is irrational because there is no ratio of integers that equals pi. So Well, now of course it took a while before people discovered that there were such things as irrational numbers, and let's just say that it caused a lot of controversy. All right, so what they're going to show you in this video is a demonstration as to why the square root of 2 is irrational and how that led to problems. This was discovered in ancient Greece, by the way, by one of the followers of Pythagoras. Oh, does that ring a bell? Our old friend Pythagoras? What was he responsible for, among other things, that you know very well?
Pythagorean theorem.
That's right. Our old friend, the Pythagorean theorem, which nobody forgets. It's one of those things that stays with you forever. How does that work again? Let's see. If you have a right triangle, oh, somebody wants to guess Pythagoras? That's the one. Yes, exactly. So we have two sides, A and B. What is the name of this side, by the way? Starts with an H. I bet you know.
Hypotenuse.
Hypotenuse. That's right.
Pythagoras was a really interesting dude. He had like a whole cult following and stuff.
He had a cult following, and when his followers discovered that the square root of 2 is irrational, they actually tried to keep it quiet because they were really worried that the mobs, as they called them, would actually revolt when they found this out. Because, well, you'll see why. They'll talk about it in the video. Okay, I don't know what it's doing now. I accidentally asked it to save this file, but that's right. Hypotenuse. And of course, the relationship that he explained to us was that a squared plus b squared equals c squared. So they're going to use this result to explain to us why the square root of 2 is irrational and how that so upset their worldview that, again, they tried to keep it quiet. They didn't want to damage Pythagoras's reputation, or at least they were afraid that that's exactly what would happen. All right. God, what happened there? I noticed that you got to be careful with this stuff. All you need is one bad move by your pinky, and all of a sudden you're erasing stuff, you're creating crap. This is extremely annoying.
That's interesting because, like, on first thought, having not watched this video and stuff, I would think that, like, the square root of 2 and, like, c squared could be explained by the ratio of a squared plus b squared.
Oh no, let's watch the video first. I'm just realizing that something went horribly wrong with my PowerPoint slide here. I was fooling. I must have done something I shouldn't have, because all of a sudden it started copying the Pythagorean theorem onto every one of those slides. Let me just get it back open again real fast, and then we'll watch the video. That's the thing. When you're not careful, I mean, like I've noticed, like if you're not careful with your mouse, like just last night, this happened to me. I accidentally dragged one file into another one, and I had no idea what happened to it. And it was very frustrating because the mouse, it does sometimes what it wants to do. Oh, I'm looking at the wrong one. No wonder. Hold on a second. I have to go recover my file here, and then we can carry on. Oh, okay. Maybe we'll talk about it later on, because I'm Mr. Non-technology. If there's ever been a person who does not understand technology and who's constantly victimized by it, it's me. Okay. So that's the thing about technology. It sort of senses when you don't get it. And then it tries to take advantage of you by breaking down whenever it has any opportunity. You probably noticed that yourselves. Okay, let me just find out where we were. Yeah, I didn't want to lose all the stuff that I was writing. So yeah, it is like, you know, it reminds me of, like, it's like having a pet lion. Um, it'll eat you as soon as it gets its first opportunity. So you want to watch it when you use technology. There we go. So, okay, so this is where it screwed up. It suddenly lost its mind and said, hey, I want to mess with you. And then the Pythagorean theorem is that a squared plus b squared equals c squared. And this is, again, the heart and soul of their proof that the square root of 2 is irrational, which they found to be very disturbing. So, all right, let's find out why. So let me send you that link. I'll post it in the chat room. All right, if it lets me. Oh no, it went to the wrong place. All right, let's try that again. All right, there it is. Let's check this out. Let me first turn off my screen sharing, and then let's carry on. I'm sure you'll like this.
Professor, I think like I'm not sure if you messaged the link to the entire group. It's to me privately.
Oh, I know, but then I sent it again a second time after I noticed my mistake.
Oh, awesome. Good.
Nice. Okay. All right, are we done?
I have 1 minute.
Okay, good.
So how does this apply to the Fibonacci number sequence? Because like they started to draw the Fibonacci number sequence as a series of triangles using the length of the, like drawing it down. You know what I mean?
Are those the Fibonacci numbers?
I don't know. It just was like a very
No,
similar shape.
It did, yeah, but the Fibonacci numbers, let me just remind you what they look like. Yeah, Fibonacci's numbers do show up in a lot of interesting places, and but the Fibonacci sequence itself,
Are all the, like, is the golden ratio always rational?
the golden ratio is irrational because it's 1
Mm.
plus radical 5 over 2. As a rule of thumb for the radicals, if you take the square root of what's called a perfect square, like 1, 4, 9, 16, 25, these are all called perfect squares because their square roots are integers. If you take the square root of any of these, you're going to get an integer, which is by definition a rational number. But it turns out that if you take the square root of any other number, it's irrational. Okay, and so that's just the way it works. These are all rational. All the remaining square roots are irrational, and so because radical 5 is irrational, adding 1 to it and dividing by 2 does not change that. This is irrational. This is the Greek letter phi we often see it listed as. And it's approximately equal to 1.61802, I think. And so the interesting thing about that is if you look at the Fibonacci sequence, which, by the way, each term starting with the third term is the sum of the previous two terms. If you calculate the ratios, here we go. You know what? I'm still working. It says raise hand, and then I don't know what happens next. It just sort of disappears. So whoever raised their hand, go ahead and ask your question.
Well, I apologize to interrupt, but I found it really interesting in a way that they conveyed that how there are universal rules regardless if it's in the field of math or not. So like it mentioned how, in music, it's always comprised of theory. So I found it really interesting how regardless of if we want to ignore it or not, math will always be a part of our lives.
That's right. That's a very good point. Yes, it shows you that no matter what's going on, somehow math is involved. And that's a very good point, especially it's good for people to hear that, people who are not that crazy about math. It's everywhere, isn't it? It's hard to imagine any lifetime. I mean, unless you live in a desert island, and even then, sooner or later it'll come in handy when it helps you figure out how to, for example, crack open something like a shell of a clam that you're trying to eat. Math is everywhere. Anyway, but if you take the ratios of consecutive Fibonacci numbers, these will converge to the golden ratio in the limit. So that's the connection there. I don't know if there's any connection between this and Pythagoras, though. But anyway, but yeah, you can see that it really upset the worldview of all those Greek mathematicians because they thought everything in nature was composed of perfect circles and perfect squares and all the rest. And these irrational numbers essentially contradicted those views. And so that made them very, very uncomfortable, which is why they were reluctant to share this with anyone else. And so they did keep it a secret for a long time. But eventually, all this came to light. And it was, in fact, developed by the followers of Pythagoras, who, like you said, somebody mentioned earlier, he was definitely a cult figure. People would follow him around, trying to gain words of wisdom from this great man's lips. You never knew when he might say something profound, and they'd all want to be there to hear it. All right. So, okay. Well, let's see. So I see it just says two people raise their hands. All right. Well, if you want to ask a question, go. Oh, there it is. Look at that. There's a little hand there. I never saw that before. So, how about Christian? Do you want to ask something? Look at that. I swear I never noticed that before. There's little blue hands in here. So we've got Christian and Solomon apparently both wanted to say something.
So we just had our hands up before, but we didn't
Oh,
take them down, so they were just still
oh,
up.
I
Yeah,
didn't.
my apologies.
I'm still learning this technology, as you can tell.
You're good. One quick thought though, I guess just a comment really is I think it's really fun to me that like the ancient philosophers all relied upon reason to answer um
Yes, they
like,
did.
their existential crisis, and like it's kind of ironic and paradoxical that math ends up being illogical, even though it's like the most logical form of explanation humans have encountered, you know?
Yeah, it has some strange contradictions, like the idea of infinity, is there being different sizes of infinity. That's a tough one to wrap your mind around. There are different degrees of infinity. You can have two infinite sets, and one is completely contained within the others. Like here's a perfect example. The hold on. If you we can define the so-called natural numbers. You can see why they're called natural, because they're used for counting purposes. This is an infinite set, and yet if you define the integers as -3, -2, -1, 0, 1, 2, 3, it should be clear that the natural numbers are a subset of the integers, and yet they're both infinite sets. So how is this possible? So yes, we do run into these bizarre contradictions sometimes. So yeah, math is as logical as you're going to get, and yet it still itself runs into these issues. And so a lot of mathematicians think about this stuff at very great length, and it's a very interesting field. Let's just put it that way. But yes, in the early days, those Greek philosophers were all mathematicians. They were considered to be part of the same thing. I mean, mathematics was simply another way of expressing philosophy. It wasn't meant to be independent of math. All right. Well, anyway, enough of all that deep thinking. Let's go back to what we were doing with some practical applications. But I actually do have one video which talks about the different levels of infinity. Maybe we'll look at that at another time. And also another one which gets involved with discussing proofs. There's one proof in particular that has eluded mathematicians for a very, very long time. And that has to do with this thing called the Goldbach conjecture, which we'll see this video later on. It's a very interesting idea. Basically, all it says is this: for any even number, or any even number greater than 2 can be expressed as a sum of two prime numbers. So for example, 8 could be written as 3 plus 5. 16 could be written as 3 plus 13, et cetera, et cetera. So the problem here, though, is that no mathematician has ever been able to prove that this is true for every even number. What they've been able to do instead is, with a computer, generate all the even numbers and find examples of a sum of primes. And the number they've gotten up to by now is like some preposterously large number. It's so enormous, it's hard to even imagine it. But that's not the same thing as proving that this is true for every even number. They've been able to churn through all these even numbers up to these enormous values and show that in each case there was a pair of prime numbers, but it's not, again, the same as proving it. So that's why it's still called a conjecture, because it may not turn out to be true. Okay, so there's a video that I'll show you later on, which actually talks about this, but more in the context of how proofs are done and what is required for a proof. But anyway, so I thought you'd find that interesting. So anyway, let's get back to where we were with the so-called composition of functions. We're going to create what are called composite functions, where one function is a function of another one. And so we'll start with these four basic cases. This notation means just take the sum of two functions, f of x and f of g of x. This one means take the difference. This one means multiply them, and this one means divide them, which so far these are not that difficult. But don't worry, we'll get to some cases that are actually quite challenging. So why don't we look first at some simple examples? All right, so like what? How about this one, or these two? Why don't we go through all of these cases with these two functions? And let me copy these so we never have to keep scrolling back and forth. We'll start with, let's see. Here we go. So just to remind you what these functions are, in this case, it couldn't be any easier. You literally just add those two together and combine them. And by the way, just by convention, whenever we have an expression like this, which is called a polynomial. Whoops. Okay, let's try that again. Polynomial, which simply means many numbers. You'll notice that we write them in descending order of the exponent. And of course, here there's an implied 1. So we start with x squared plus x minus 1. This is the normal way of writing a polynomial. All right, well, that was a breeze. How about if we try to subtract them? All right, so let's just put them up here just as a quick reminder. Are we allowed to do that? Yes, of course. So we've got, when we consolidate these, now remember here, don't forget to distribute that negative across all the terms in that set of parentheses. So we've actually got, let me write the intermediate step here, x minus 2 minus x squared minus 1. And then, of course, we'll consolidate all the like terms. We have 1x squared, one term with x squared in it, one term with x, and then we have these two constants, which give us negative 3. Okay. How about now multiplication? This is where it gets more interesting. We're going to apply, you might recall this from your travels, a technique here called FOIL. All right, who remembers what those letters stand for? First, outer, inner, less. Yes, exactly. It's a perfect mnemonic device because it's impossible to forget. That's it. You know it. So what does that mean? Well, first would be the product of these two terms. Outer would be these two terms. And that's going to give us x. Inner would be these two terms. Okay, and then finally last would be these two terms, which is negative 2. So I'm going to consolidate. First, I write them all out, and then in this case, I can't really combine any of them, but I can change the order. Remember, we want them, the exponents to be listed in descending order. So I'll rewrite this as x cubed minus 2x squared plus x minus 2, and I'm done. All right. So we've saved the best for last, well, the most challenging one, which is division. All right, now here we have to watch it because as always, we have to make sure we don't inadvertently end up with division by 0. But here you can see we have a very simple case. Realistically, there's no way to simplify this. Sometimes you can, but not here. All right, and this is the final result. That's it, we're done. All right, but now what comes next is just a little bit more challenging. We're going to take functions of other functions. We're not just going to algebraically rearrange them somehow. We're going to actually take a function of a function. And these types of functions are known as composite functions. You may recognize this notation. This little circle tells me that what I'm actually doing is taking the f of g of x. And then here, this notation represents g of f of x. So now we're going to find out how in the world do we figure this out. It's actually a lot scarier than it looks. Well, actually, sorry, it looks a lot scarier than it is. Don't worry, you'll see in a second how this works. All right, let's take a look at this. Let's do some examples. This is the best way to do this. All right. So anyway, just checking. I'm looking for frightened faces. I'm not seeing any. That's a good sign. Okay. All right. So let's put this away. Let's try some of these. So again, let's try these two now. And what we're going to do is actually, let me copy this. By the way, if you have Windows, this snipping tool is awfully handy. It comes with Windows if you've never used it. Watch what it lets me do. I can copy anything I want, and I can paste it anywhere I want. Look how nice that is. Oh, well, here it turns out not to be necessary because I've rewritten them. But let's say I forgot to do that. Look how easy that is. Oh, my God. So anyway, so what we have to do is this, f of g of x. So what you're basically doing is everywhere you see x in this function, replace that x with g of x. Okay, so in this case, the original function was just x minus 2. So I'm going to replace x with this. So this is a particularly simple case. So I end up with x squared plus 1 minus 2. And then when I get rid of the parentheses, it simplifies very nicely to x squared minus 1. So this is written in two different ways. F of g of x, or like this is probably more common. This way it's clear that you have a function of a function. All right. Well, that wasn't so painful. What do we do now? Oh, yes, we have a chat. Goth, that's right, g of f. We're going to work it backwards with the same functions. And of course, we're not going to get the same results. This time, within g of x, this x squared becomes g of x squared. Okay, so in other words, the x itself is what's being replaced with g of x. Don't forget about the square. Oh, I'm sorry, I wrote it backwards. This should have been f of x. Because it's g of f, this should be f of x squared. That's better. Okay, so yes, here it is right here. So x squared becomes f of x squared plus 1. And now f of x was this, which when I square it right here, and I still have that 1. And x minus 2 squared, you can apply FOIL to this if you want to. And you'll have f o I, whoops, minus 2x and last would be these two. Minus 2 is 4. And these you can consolidate into x squared minus 4x plus 4. And that's what we see here in these parentheses. And of course, we still have this 1. And that, when we bring these together, we end up with x squared minus 4x plus 5. Now, by the way, I just wanted to quickly show you another approach to multiplying two expressions together like this, which is more general than what the hell just happened? Oh my God. It just changed all the formatting. Man, my computer is having a rough day, I have to tell you. I don't know what in the world I did, but look what it did. It changed the background. Oh, that's pretty uncool. I'm getting pretty annoyed here. No, I don't want that to stay. Well, I don't know what just happened there. All of a sudden, the formatting was just completely screwed up. So we'll just have to carry on with what we were doing. That is unbelievable. That's the second time today that it's really screwed up. All right. So, all right, let's carry on with this one. So, yes, x minus 2 squared, after you apply FOIL, is x squared minus 4x plus 4. And that gets substituted in here. And this is our final result. Okay, now the next thing we want to be able to do is evaluate these functions, which means I want to not only have the actual composite function, but I want to evaluate it at a specific value for x. All right, so in other words, when I'm done, I need to have a number. All right, let's try this one. So we've got f of x is x plus 7. G of x is 2x squared minus 3. We want f of g of 1. In a way, this actually makes things easier because look what happens now. G of 1 is 2 times 1 squared minus 3. And that's going to give me 2 minus 3, or negative 1. So therefore, f of g of 1 is the same thing as f of negative 1. And since f of x is x plus 7, f of negative 1 would simply be negative 1 plus 7, which is 6. So that actually made things a little easier, I think you'll agree, because we're looking for a very specific value rather than a function. And yes, that's exactly how that worked. So what we did was we substituted 1 for x in g, and then only then did we replace our x's with negative 1, and we wound up with 6. Okay, so it's fun to create these functions, but ultimately what we really are probably looking for is a specific result. Okay, depending on what we're trying to do. Now, how about g of f of 1? All right, so just a quick reminder, this is f of x, this is g of x. So first I evaluate f of x when x equals 1. I replace the x with 1. So f of 1 is 8, which means that g of f of 1 is the same thing as g of 8. Look how easy that is. So go to g of x. Every x you see is replaced with an 8. And so we wind up with 2 times 8 squared minus 3, or 2 times 64 minus 3. And the final result is 125. So actually, in a way, these evaluations make our life a little bit easier. Instead of getting horribly complicated functions, these are nicely reduced to a constant. All right, let's see what's next. Oh, domains. Oh my God. Now we have to figure out the domain of this composite function. Now that's going to be a bit of a challenge. All right, so here we have two functions. Oh, good. Yes, that's a very good skill to have. Yes, if you can do this, then you are good. You are mastering that skill if you don't need anyone else to show it to you. Good. I'm glad that things are going smoothly because, well, I mean, of course, the later content will be more complicated, but this is a good start. Very good. I'm glad you told me that. Anyway, but now this one's pretty tricky because you can see the domain here is basically everything except 1. Down here, the number that causes trouble for us is 2/3. If you plug in 2/3 for x, you'll get 2 minus 2, which is 0. So, but what we're really interested in is not the individual domains, but the domain of the composite function. So that means, well, we already know that the domain of g of x is every number except 2/3, and for f of x, it's 1. So what does that tell us when we bring them together? So it means that we don't want anything to cause f of x to be equal to 1. So what we're going to do here is claim that we don't want 1 to be fit into g of x either. So we're going to set this equal to 1 and solve for where x equals causes this to happen. So we're going to solve for this. And we end up with 2. Now, actually, the way this is working here, I think it would be easier here, in my opinion, to just actually solve for this f of g of x and then figure it out directly. This technique can work, but I think this is more straightforward. So let's do it this way. We're going to consolidate. So for f of g of x, we're going to end up with (5 over g of x minus 1). Okay, so remember what this means is take each x and replace it with g of x. And so now we're going to need to do a lot of algebra, of course, to simplify this. And when we do, let's see what happens. Now, here we have a ratio in the denominator. How do we consolidate these two together? We can rewrite this one in many different ways, but what we're looking for is a common denominator. That way we can actually combine these into a single fraction or ratio. And, all right, I'll give you a minute to catch up. All right, are we ready? So in other words, what I've done here is I've created a common denominator, so we end up with this. And now, by the way, I want to remind you of a very important result here. If you have a ratio like this, let's say A and B are, and C and D are any real numbers, this is the same thing as A over B times D over C. So you could actually rewrite this as 5 times 3x minus, 6 minus 3x. Oh, no, my fault. No, not yet. No, I'm reversing. I'm taking the inverse. 3x minus 2 goes here. And then this stays down here. Okay, and that's why it looks like this, because of this property right here. It just so happens here that in the numerator, the b is 1. So if you have a over c over d, this is the same thing as a times d over c. And that's what's happening here. So I reduce it, rewrite it, and I write it out like this. Now, we know that we do not want x equal to 2. So x equals 2 is not in the domain of f of g of x. And so that was pretty straightforward. This is what we were looking for. So the domain of this thing is everything except 2. So that approach, in my opinion, is easier than what we were just trying to do a minute ago, where basically, I don't know, I don't like this approach very much. It doesn't, to me, make a lot of sense. So why don't we stick with this approach? Just figure out the function and then figure out the domain in the normal way. Oh, it just seems to me a lot cleaner. And we end up, as you can see, seeing quite correctly that x equals 2 is not in the domain, but every other real number is fine. Okay. All right, now decomposing a composite function, we're working this backwards now. We start out with the assumption that f of x equals radical x minus 8. And we can actually break this up into a composite function if we need to for some reason. And so in other words, we want to rewrite this as f of g of x. How can we do that? Well, let's see how that works. Since f of x equals radical x minus 8, well, actually, here's what we're going to do. I'm going to change the notation slightly. We're going to claim that this is equal to g of h of x. Okay. Just to avoid confusing the f's with each other. So if we call g of x radical x and h of x x minus 8, then clearly that means that this is equal to radical h of x, which is, oh yeah, here we go. So it means that f of x could be thought of as a composite of these two functions. So basically, we're working this backwards. This composite function, we're essentially creating one from two individual functions. And you can prove it just by plugging everything back in, and you can see that, yes, indeed, this is our original f of x. Okay. All right. Well, you know what? We didn't have our second break, and I think We've gotten a lot done today, in spite of all the technical issues that I keep running into here. You can see how the technology absolutely does not like me, and it's constantly messing with me. I'm not imagining things, am I? You saw it yourselves. But in spite of all of that, we got through all this good material. Now, what I would like to do, though, is going forward, each class, I would like to work on at least a few problem sets. So let me just quickly double check something here. It messes with all of you. That's true, but it seems to mess with me more because I don't understand it. And it knows that. All right, so I'll tell you what, let's do this. From now on, let's get into the habit of working on problem sets every week. I don't think we've done these yet. So let's do this. Let's agree that between now and next week, well, first things first, I'll make sure all the videos are actually where they belong in the YouTube account. Still don't know how that happened, but you should watch, if you need to, rewatch the videos. You can reread the slides. And for this week, why don't we agree to do these first two problem sets? I think we're ready for these. Now, I'm not collecting these and I'm not grading them. We're going to work on them together and make sure we're all getting the right answers. So looks like we're ready for the first two, and then we'll take it from there. All right. So your only job now is to make sure you know what's going on. In other words, catch up with the slides, catch up with the videos, but also work on the first two practice problems. See, now I know the secret. There's a little blue hand over here. All right, go ahead.
Those are the first two. Just want to make sure I know like where to find them.
Yes. Oh, they're on Moodle. Let me go back to Moodle real fast. It should
I think I do, but I'm just gonna look right now too. I had some trouble finding things before. So this is chapter 1, practice problems, part 1.
Part 1 and part 2, yes.
Part 1 and part 2.
Right.
So
Exactly.
we're doing part 1 and part 2 by next week.
Yes, by next Wednesday, yes.
Okay, thank you.
All right, and then we'll carry on with the new material. There's plenty of it. Don't you worry about that. We got plenty of, but we have plenty of time as well. We got 16 weeks, and we're not going to have any in-class exams, as you know. So that frees up 2 full sessions. So don't worry. By the time we're done, we'll get a ton of great material finished. But I do want to make sure we work on these practice problems. And then also, I'm still looking at this Delta math thing. I'll remind you about that. Once it gets set up properly, what I'm going to have you do is work on those maybe during the weekends or whatever, just to make sure that you really and truly get what we're doing. But that's a separate thing. Right now, let's just focus on the practice problems. Okay, is that a hand that was never put down, or do you have another question?
I have another question actually. What slide did we end on today?
Oh, that was slide. This is actually the end of one. I typically break up the PowerPoint slides into sections. This is section 1A. We are completely done with 1A, which is slide 160. All right. So there's more. There's 1B, which is, well, it doesn't seem to be here anymore. I'm telling you, this is not my day with the technology. I definitely had it open before. We're going to look at some basic geometry in effect. I mean, we're going to see how changes to these functions affect their graphs, but then we're going to get through that fairly quickly, and then we're going to look at some other important concepts. All of this is part 1B. Okay. And then we'll be ready for chapter 2, which I haven't posted yet, but chapter 2 is about, I've forgotten already. I think it's linear functions. Yes, all about linear functions and solving systems of simultaneous equations. All right, very interesting and especially useful for many applications like finance or economics, let's say. All right, so I guess that'll be it for today. And so I'll see you all next time. All right. Unless you have any more last minute questions.
Thank you. Have
Thanks,
a good
Professor.
You're welcome.
Have a good one.
All right.
you.
Thank you, Professor.
I do actually, Professor. Hello.
No, I'm here.
Okay. Yeah, I was wondering if you're not busy later, if you're able to help me with solving practice problems one, because I was actually having trouble with it. I tend to overthink when I'm doing math. So
Oh, all right.
yeah.
Well, today's not really a terribly good day. Maybe later in the week.
Okay.
I'll tell you what, send me an email and we'll figure it out.
Okay. All right. Thank you for your time,
Okay.
sir.
right,
Enjoyed the
you're welcome.
lesson. Have a
All
good
right.
night.
Excellent. All right. See you later.
See you.
All right. Bye.